Today I'm going to walk you through the process of estimating ancestral protein sequences using MegaX. A common reason to reconstruct ancestral sequences is to synthesize ancestral proteins in order to compare those ancestral proteins' physical properties with the properties of existing proteins. For this example, the goal today is going to be to estimate ancestral protein sequences of the EBGC protein of E. coli. The data that we start with is shown in the Alignment Explorer window of Mega. The data consists of the coding sequences of 40 homologs of EBGC. The homologs include 36 sequences from 3 orders of the gram-negative bacterial kingdom, 4 sequences from 3 orders of the gram-positive kingdom. This diversity of sequences is going to become important shortly. The first step that we have to do is to align those sequences in order to bring the homologous sites into the same column. We'll do that by using the alignment program Muscle. We'll go to the Muscle icon, pull down and choose Align by Codons. It is essential to align the sequences by codons, not by DNA. These are coding sequences that we are aligning. Alignment introduces gaps representing historical indels into the sequences. Alignment by DNA can introduce gaps within codons, resulting in nonsense protein sequences. Alignment by codons introduces gaps only between the codons, maintaining the integrity of the codons and of the reading frame. When we choose Align by Codons, shortly the aligned sequences appear in the alignment editor. You'll notice that wherever there are gaps indicated by the dashes, there are gaps of 3. This maintains the reading frame. Having aligned the coding sequences, it's now necessary to export the alignment in a format that Mega can use to estimate a phylogenetic tree. Go to the File menu and choose Export Alignment in the Mega format. And when you do that, you're going to save it, in this case, as a file, which will be we'll call ebgc.meg. That becomes the input file for the next step. Having saved the alignment as ebgc.meg, we'll go to the main window and open that alignment, that ebgc.meg file, in the main Mega window. When you've done that, you'll see the little TA icon appear, and that means that you have successfully opened the .meg file. The next step is to make a phylogenetic tree from those sequences. We're going to make a maximum likelihood tree, and the first thing that we have to do is we have to choose a model for making the maximum likelihood tree. Go to the Models menu and pull it down and choose Find Best DNA Protein Model and click that. After a minute or so, you will see this window appear showing a list of all of the models in the order of the best model for this data set. The purpose of using the models function is to pick the best model for this particular data set. It won't always be the same model. The models are listed in the order of best to worst. In this case, the best model for these data is GTR plus G. We'll talk about what that means in just a moment. But keep in mind we're going to use the GTR plus G model to estimate a maximum likelihood tree. The next step is to go to the phylogeny function and pull down the menu and choose Construct Test Maximum Likelihood Tree. Doing that brings up the Preferences dialog. Maximum likelihood is already indicated as the method. It's doing nucleotides, which is good because that's what our data are. The things that we have to pay attention to here are model method and rates among sites. In the model method box, you'll click at the end and that will display a little menu, And one of the items you can choose there is General Time Reversible Model. That's what the GTR in the model description stood for. GTR stands for General Time Reversible Model, so we'll choose that. The next thing to do is make a similar choice for rates among sites. There are a number of choices. The model was GTR plus G. G stands for gamma distributed. So we'll choose gamma distributed. The other thing we want to be sure is that we've got use all sites selected, and that we're going to use all the codon positions, at which point click the OK button. And in a minute or so, a tree is displayed. This tree shows branches and nodes. These internal nodes, the vertical lines, represent the hypothetical internal ancestral sequences. This tree appears to be rooted. That is, it appears that the leftmost node represents the ancestor of all the sequences in here. That appearance is misleading. Maximum likelihood does not estimate rooted trees, it estimates unrooted trees. But the tree has to be drawn with some node at the left, and the tree is drawn with what's called midpoint rooting, just to give some plausible look to the tree. In order to see a more realistic appearance of the tree, an unrooted tree, we need to go to this little icon right here, pull it down, and choose radiation. This shows the unrooted tree. I emphasize this is exactly the same tree you were looking at before. It's just drawn differently. And it's drawn this way to bring to your attention that we really don't know where the root of this tree is. We have to figure that out. And if we're going to estimate ancestral sequences, we have to have a rooted tree. Rooted trees have direction, so we know which nodes are ancestral to others. We need to explicitly root the tree by using an outgroup. The existence of an outgroup implies the existence of an ingroup. And an ingroup is a set of sequences that are more closely related to each other than any of them is to any of the outgroup sequences. The sequences from the ingroup gram-negative kingdom are circled in black, while those from the outgroup gram-positive kingdom are circled in red. We know that all the gram-negative sequences are more closely related to each other than they are to any of the gram-positive sequences. We must therefore put the root onto the branch joining the in-group gram-negative to the out-group gram-positive. The red arrow indicates that branch. We're going to go back to the original view. This is just a different view of it. And we're going to root the tree by placing the root on that branch. The branch that leads from the gram-positives up here, the gram-negatives down here, is this branch here. Select the rooting tool, and the appearance of the cursor changes so it looks like this. Click anywhere on this branch, and you root the tree. In this particular case, it's not going to change the appearance of it. But now the tree is actually rooted. And we can say that this node is ancestral, for instance, to that node. Having rooted the tree, the next step is to identify the nodes. In the View menu, choose Show Hide and pick Node IDs. When you click on that, each of the nodes is labeled with a number. There are 40 tip nodes, nodes out here that have names, and they are numbered 1 through 40. The remaining internal nodes are numbered 41 and above. Why is it necessary to number the nodes? because eventually we're going to be wanting to talk about these internal nodes, and we have to have some way to refer to them. We'll refer to them by their numbers. The next step is to go to the Ancestors menu and choose See or Show Most Probable. When you do that, each of the nodes is labeled with the most probable base at that node for the position in the alignment that is shown here. So this is the first base, and if you'll notice, every one of them has an A, which is reasonable. These are coding sequences. They all begin with ATG. The next step is to go right back to the Ancestors menu and choose Detailed Text Export. Doing that is going to save a file that has all of the information about the most probable base at each of the sequences at each of the sites in each of the sequences for each of the nodes, each of the internal nodes. When we choose that, we bring up a save dialog, and we'll give the file that we're going to save the name ebgc-anc.txt. Anc just indicates ancestor, and it's a good way to remember what you've done. When that file is opened, it looks like this. I emphasize that this is a text file. It should not be opened with a word processor such as Word or WordPerfect. It should be opened with a text editor such as Notepad or Notepad++ for Windows, or Text Wrangler or BBEdit for Mac, or gedit for Linux. When you open the file, you'll find it's a very long file. It lists each of the internal nodes, starting with node 41, and for each site in that node, each position, it lists the probability that that is an A, a C, a G, or a T. So if we look at this, we can see the first three bases are A, T, G, just as we would expect. Looking at node 41, at least the first 19 positions, it looks as though at each site we're absolutely certain what the most likely base is. That's not necessarily the case all the way through. We could scroll further down and find, for instance, node 49. And for node 49, we'll still see very high probabilities for the first few, but when we come down here to say node 12, or site 12 in node 49, the probability of that being an A isn't 1, it's 0.86. And that is going to continue. Some sites will know to a high degree of certainty what the base is, and for some we won't know it all that certainly at all. This ebgc-anc.txt file isn't terribly useful as it stands. What we really want is the best estimate of the entire sequence at each ancestral node, along with some estimate of the reliability of that sequence. Now we could get that by just looking in that sequence file at the most probable base and writing it down, but we'd certainly make many, many mistakes in doing that. I've written a little program called extantseek mega that processes that ebgc-anc.txt file to provide exactly the information that we need. The program is available from the Phylogenetic Trees Made Easy website at this address here. If you go to that site, this is what you'll see. And at the very bottom, down here, there's a button labeled Student Resources. Clicking that button takes you to another page, and you'll see this. The buttons that you're interested in here are the orange ones. These will download a set of files, and which set you get depends upon what operating system you have. If you are running on Linux, click the top button. On Mac, the middle one. On Windows, the bottom button. When you click that, a file will be downloaded to your computer, a zip archive, shown here. The file will be called something like ptme companion files, in this case mac.zip. Double-clicking on that file creates a new folder with the same name. That folder contains a bunch of folders, one of which is utility programs. And inside the utility programs folder is extantseek mega, the file for the program of interest. You now have to install that program on your computer. Installing it is really easy in the Mac and Linux system. You simply have to drag the file into the /usr/local/bin folder. If you're a Linux user, you'll know where to find that folder. If you're a Mac user, all you have to do is, in the Finder, in any window, enter Shift-G, and in the dialog, put USR local bin folder, and click it, and it will take you to that folder. Drag your file into the folder, and it's installed. Windows, it's a little more complicated. For Windows, you'll have to create a folder named bin directly on your C drive. That is, not within any other folder. Then you have to set the path environment variable to C:/bin. Then you can drag the file into that folder. If you don't know how to set the environment path variable, you can either see Appendix 4 in Phylogenetic Trees Made Easy Edition 5, or you can email me at barryghall@gmail.com, and I will send you a PDF file that shows precise instructions, including lots of screenshots, to show you how to complete installation of Windows by setting up your path environment. Having installed the program, the next thing to do is you have to run it. In Terminal, for Mac or Linux, or Command Prompt in Windows, navigate to the folder containing the detailed export file. In this example, that file is ebgc-enc.txt. And enter extantseek mega, the name of the program, space ebgc-enc.txt, the name of the input file, and hit return. If you don't know how to navigate to a folder in the terminal program or in Command Prompt, that information is contained in the description of how to set a path variable, and you can write to me, whatever your operating system is, at barryghall@gmail.com, and I will send you detailed directions for how to do the navigation. So you start the program by entering this, hitting return, and in less than a second, the program will create a folder named, in this case, ebgc-enc.txt output files. And into that folder, it will write one file for each internal node. That is, there will be a file for node 41, a separate file for node 42, etc. Those files include the ancestral DNA and protein sequences and probability information about the sites in just the format that makes it useful to us. This shows the ebgc-enc.txt output file folder, and in it all of the files for the various nodes. So now the question is, what ancestral node do we want to know the protein sequence for? Well, I happen to be interested in E. coli and its close relative Salmonella. So I'd like to know the protein sequence for the common ancestor of E. coli and Salmonella. Going back to the tree, here's Salmonella, and I work my way back along the branches all the way until I find a node that will allow me to go up and work my way back out to E. coli. This node is the most recent common ancestor of E. coli and Salmonella, and it's indicated with a red arrow. This is node number 62. That's why we numbered the nodes, so that we can identify them. So the next thing we want to do is open the node 62 file in a text editor, and this is what it looks like. At the top we have the node name, and then it looks very much like that file that was output by the Megger's Ancestor program. It lists the sites, A, C, G, or T, the probability that that site has an A, C, G, or T. Then it lists the most probable base at that site, at the first site, and its probability. We could read the entire DNA sequence just by reading down this column of most probable base. That really isn't terribly handy. So what we'll do instead is scroll down to the bottom of this list of most probable bases, and we'll see the most probable ancestral DNA sequence is this. Right below that is the most probable ancestral DNA sequence without gaps. They look identical because there's no gaps in this region. This is in a text editor, and text editor allows you to go way, way out without having any line wrapping, so the sequence goes way further out. Immediately below that is the accuracy score for this sequence. The accuracy score is 0.936. That score is defined as the average probability of the most probable bases. So that's an average of the values in this column. That is not the probability that this sequence is correct. That probability would be obtained by taking the product of all of these numbers. And it's a very small number, 9.5 times 10 to the minus 16th. This is just the average probability that a base is correct. But we weren't really interested in the DNA sequence. In the end, we're interested in the most probable protein sequence so that we can have that protein synthesized for us. Immediately below all this information about the DNA is information about the protein sequence. We're still looking at the file for node 62. The headers of the columns are a little bit different. The first column is the name of the most probable amino acid. The next is its probability. The next column is the second most probable amino acid and its probability. And the final column is the ratio of the two. The most probable amino acid is M for methionine. The second most probable amino acid is A. Its probability is 0. The ratio is, of course, infinity. Here I'm going to represent infinity by 9999 because text editors don't show a little infinity symbol. So we can go down looking at each of the amino acids, and notice that they all have pretty high probabilities, and the ratios of the most probable to the second most probable are all pretty high. The worst is 10, until we get down to K. The most probable amino acid in here is K, but its probability is only 0.63. The second most probable is Q. Its probability is 0.33. Doesn't give us a tremendous amount of confidence. The ratio is 1.91. So that's less reliable. Going on down here to the S is only 0.49 probability, and T is 0.374. The ratio of those two is 1.31. Any site where the ratio of the most probable to the second most probable is less than 1.5 is flagged as unreliable. That's an arbitrary choice, and you can think about it as anything that you want. So we can get the most probable amino acid sequence by going down that column. And if we scroll all the way to the bottom, that is exactly what we see. The most probable ancestral protein sequence is this, including one position where there's a gap. The most probable ancestral protein sequence without gaps is that. And that's what we're really after this whole time. This is the most probable sequence of the ancestral protein that is the common ancestor of EBGC from E. coli and Salmonella. That's the sequence that we will send off to a manufacturer to have them synthesize the protein for us so that we can compare its properties with the properties of existing proteins. The accuracy score for that sequence is 0.948, slightly higher than the accuracy score for the DNA sequence. Again, that is not the probability that that sequence is correct. The probability that the sequence is correct would be the product of all these numbers, and that would be 6.5 times 10 to the minus fifth, which is still considerably higher than it was for the DNA sequence, where it was something times 10 to the minus 15th. So we've got a sequence and an estimate of its accuracy. Next question we have to ask is, how good is that estimate? How accurate are the ancestral sequences that are calculated by MEGA and this program that I wrote? We can't tell that for real data because we don't know what the ancestral sequences were. But based on a set of evolution simulations in which which sequences are evolved in the computer from some starting point out to a whole tree, and we know the sequences of the internal nodes, of the ancestral nodes, we can compare the known sequences of the internal nodes with those that are estimated by this program to ask, how accurately does the program actually estimate the sequences of the internal ancestral nodes? For DNA sequences, the estimates were about 90% accurate. For protein sequences, they were better than 96% accurate. extantseek MEGA's accuracy score overestimates ancestral DNA sequence accuracy by 2.7%, but it underestimates ancestral protein sequence accuracy by about 0.4%. So we can summarize the process as the first step is to align the sequences by codons. That's crucial. Don't align by DNA, align by codons. Then determine the best model to use, estimate a maximum likelihood tree, explicitly root that tree using an outgroup, then on the tree show the node labels. From the ancestors menu, choose show most probable sites, and then choose detailed text export and save a file. Then you run the extantseek MEGA program using the detailed text export file as the input file. From the resulting output folder, pick the files for the nodes that are of interest to you. Copy the ancestral protein sequences without gaps, order the proteins, and eventually pay a very large bill. The conclusion is that together, MEGA and extantseek MEGA provide a robust method to estimate ancestral DNA and protein sequences. Because extantseek MEGA identifies the low reliability sites in the protein, it's feasible to synthesize a few different versions of an ancestral protein, taking into account unreliable residues in an important region. For instance, if in the active site you've got an unreliable residue, it might be worthwhile to have two versions synthesized, one which has the most probable amino acid at that site, and the other which has the second most probable amino acid. And that is the end